All right. So it's been a while, you guys. We had holidays, we had snow days, we have a snow day today. Uh, one thing after the other. All right. Um, I don't really have any new updates for you guys about anything that's happening. The only thing I want to tell you guys is that there is online tutoring still going on. What the college did was they actually pivoted to like fully online. So you guys still have the same kind of access. I made an announcement update where you guys can see the link to, or not the link, the meeting ID and the password, excuse me, to access online. So you guys can go join anytime you want. Just to recap, the hours for online tutoring is Monday through Thursday, 11 a.m. to 8 p.m., and Friday and Saturday, 12 p.m. to 6 p.m. All right. You guys can go there to do your homework, get help with your homework, get help with the understanding of the material. No problem. All right. So I'm thinking about like I would like to do a test next on Thursday, but I feel like that's like really, really short notice, especially after we had so much time off. So I'm thinking about Tuesday. Let's do our first test. That sound good? It'll only be on the stuff that we went over so far. Awesome. All right. And you guys have your homework has been posted. Like please try and stay on top of it. All right. I know some people were just added to the class recently. Try and catch up. Look at the announcements that have been made on Brightspace. You guys can access the class recordings from there, and you can rewatch whatever you missed and knock out your homework accordingly. Okay? But before we start for today, does anybody have any questions? Nothing new from what we didn't do today, but anything from the past that you guys would like to see done? Any questions about anything from the videos that you guys watched? Oh, okay. I'll give everybody like another minute to respond in case anybody's trying to open up their web work to look at any of the material. All right, we have a brand new topic today that we're going over. Pretty fun, pretty fun. I'm not gonna lie to you. I'm pretty sure most of you guys have an idea about what this topic is. You just probably never seen it applied in this manner, but you definitely know about this topic in some way, shape, or form. All right. So let's jump into what we have for today. One second. I just want to change the brightness on my computer. All good. All right. So here's what we're getting into today. It's a new-ish topic to you guys. New-ish. All right. So we're going to be doing something called scatter diagrams and linear correlation. All right. So, studies of correlation and regression of two variables usually begin with a graph of paired data values x and y. This is similar to the points on a graph, right? Remember how we did the points on the graph with x and y is the same kind of idea, right? We call such a graph a scatter diagram. So, here we go. A scatter diagram is a graph in which data pairs, X and Y pairs, are plotted as individual points on a grid with horizontal axis X and vertical axis Y. We call the X the explanatory variable, and we call Y the response variable, right? So if you guys remember our talks about independent and dependent, same idea here, but we have new vocabulary words that we call it in statistics. All right. Anyway, by looking at a scatter diagram of data pairs, you can observe whether there seems to be a linear relationship between the X and the Y values. Okay. So now let's look at an example. All right. So here we go. Here's an example. Cool. Right. So phosphorus is a chemical used in many household and industrial cleaning compounds. Unfortunately, phosphorus tends to find its way into surface water where it can kill fish, plants, and other wetland creatures. So sad. So, phosphorus reduction programs are required by law and are monitored by the Environmental Protection Agency, right? EPA. A random sample of 8 sites in a California wetland study gave the following information about phosphorus reduction in drainage water. In this study, X is a random variable that represents phosphorus concentration in 100 milligrams per liter at the inlet of a passive biotreatment facility, and Y is a random variable that represents a total phosphorus concentration in 100 milligrams per liter at the outlet of a passive biotreatment facility, right? So long story short, let's pretend that there's a factory, right? There's a there's a input of the water going into the factory, then there's an output of the water going out of the factory, right? So what they're doing is they're measuring how much phosphorus is going in and how much phosphorus is coming out. All right. So very simply, we come up with this data pair right here, right? Now, this can appear for data pairs like this can appear horizontally or they could appear vertically, right? I think we're a little bit more used to the vertical appearance when we were plotting our points before, right? But this is how it would look horizontally. It means the same thing, right? So, for example, in the first data pair, right, I'm looking at the first one, the 5.2 for the X and the 3.3 for the Y, they go together, right? And it's as you remember, right? You go across on the X axis 5.2, you go up to the Y value 3.3, boom, and that's it, all right? So, let's say that we want to make a scatter diagram for this, right? We're going to make a scatter diagram. So here's what we're going to do. A little bit easier too. Our scatter diagrams are only one quadrant. So remember we have 4 quadrants, right? We have 4 quadrants whenever we're graphing. We're only dealing with the first one, right? When we're doing scatter diagrams. We're not dealing with the rest of them. All right? So a little bit easier. So all you have to do is just make like the first quadrant, and then that's it, right? Then what you want to do, I'm just going to put this out here because I'm not sure how long I want to make this. Put this up here, right? Then what you want to do is you want to make your axis, right? So here's a little tip with making the axis. So look at all the x values, right? And we're going to do the same thing with the y, but for now, let's start off. Look at all the x values, and I'm looking at them, and I want to know what's the biggest one that I see there. Over here, this is the biggest one that I see, 8.3. So whatever axis I choose, right? However, wherever I want to start at and however I want to increase it at, I have to make sure that something larger than 8 is captured in the axis, right? So if I want to start by zeros, I can. If I want to start at 1, I can. I can do whatever I want, right? I think I'm going to start at 1 just to show you what happens when data is shifted a little bit, right? So we do this little symbol here to indicate is think of it like I'm squishing the line together, right? I'm squishing the line together. So I'm not starting directly at 0. Let's say that I'm starting at 1. I could have started at 0. I'm just doing this for example purposes only, right? Let's say I started at 1 and I want to get to like 9 or something, right? I have to get to something bigger than 8. Now, if I want, I can go by twos, I can go by threes, I can choose however it is that I want to increase this by, right? I think I'm gonna go by twos. All right, so starting at 1, right? Well, actually, no, I should really no, I'll start at 1. So this would be 3, 5, 7, 9, and then just to make it look pretty, because I don't want to leave any space. 11, right? So I can make this X here. I didn't need all that space. Yippee, right? Now for the Y axis, same game as before, right? I'm looking at all of the Y values here. I'm looking for the largest Y value, which I see to be 7 right here, right? Now, same thing, I have to make sure that 7 and something bigger than 7 is included in my bounds, right? So again, you don't have to start at 0 if you don't want to, right? Like there is a sideways version of this thing that looks something like this, right? If you want to squish the lines together, right? Or you can start at 0 and then just increase it however you want, right? I think I'm gonna do the same kind of thing on the other side. So I'm gonna start at 0 here, then call this 2, 4, 6, 8, and just to make it look nice, 10, right? I didn't really need the 10, but just to make it look nice. And there you go. You have your axes right there, right? So using the story up here, right? The inlet is the X. I'm just trying to verify. Yep. So this is the inlet. Right? At 100, I forgot the units already. Hold on. Milligrams per liter. And then that means that for the y-axis, this is the outlet. And the same thing, 100, whoops, made a mistake. 100 milligrams per liter. All right. So now, I'll change this up a little bit. All right. So now we just have to plot these points, right? Now, we're human, right? We're not robots. I'm not expecting you to plot exactly 5.2, right? But you get the idea, right? 5.2 is just a little bit bigger than 5, right? 3.3 just a little bit bigger than 3, so just do your best. Do your best, right? Now, you guys can use dots. Me personally, I like X's a little bit more, right? I don't know. I'm just a fan of X's right here. So I like to do That's how I like to plot my points, right? So that's the first pair right here. That's the 5.2. Go across the 5.2, go up to the Y value, boom, and that's where the point would be. All right. And then so on and so forth. Do it for the rest of the points. All right. So next point is 7.3 and 5.9. So I'll go across a 7.3 where I think it would be. and then 5.9 go up to where I think that would be. Just make a little mark, right? And then do the next one, right? 6.7, 4.8, 6.7. I feel like it's somewhere like here. And then 4.8, I feel like it's somewhere like here, right? 5.9, 4.5, 5.9, 4.5. Let's say that's right here, right? Then I have 6.1, 4.0. So 6.1, 4.0 is right on the line. Okay, somewhere like there. Then I have 8.3, 7.1. So 8.3, 7.1. I think that's something like up here. Then I have 5.5, 3.6. So 5.5-ish, 3.6. I feel like that's somewhere like here. And then last but not least, I have 7.0 and 6.1. 7.0, 6.1. I feel like it's like right here. Okay, let me just verify something. I have one, two, three, four, five, six, seven, eight. It's 8 dots there, 8 dots here. All right, good. All right. In a nutshell, that's your scatter plot. All right. Any questions on this so far? Anybody? Basically, we're gonna give you some ordered pairs, and y'all gonna plot some dots. That's it. The hardest part is making the axis. You got to make your x-axis, your y-axis. Please remember to label your axes, right? You see how I label this outlet and inlet, right? Make sure you guys label your axes as well. Those are the dots, and that's it. All right. We're gonna talk about the least square line in a little bit. So let me just introduce that to you, just because I want to move on without having to go back to the picture real quick. So I need another color though. I need another color. Okay. So let's say I wanted to figure out if this scatter plot had a correlation, right? A positive correlation or a negative correlation. We're going to talk about that in a little bit. But one way that I can do that is by drawing a line of best fit, a line that it goes through all the points without actually touching the points. And then this line right here, if you guys remember equations of a line, right? Y equals mx plus b. This line right here has a slope, right? Very simply, the line has a slope. Just throwing it back for a second. Y equals mx plus b, right? This line has a slope. I'm not asking you what the slope is, right? All I'm asking you is what sign would you say that this slope is? Would you say that this is a positive slope or a negative slope? What do you guys think? Would you say that that pink line is positive or negative? Good. It's a positive slope. Oops. All right. So, very simply, if the line, right, has a positive slope, right, then this scatter plot is said to have a positive correlation. If it was a negative slope, it would mean that this scatter diagram has a negative correlation. That simple. All right. Now that we got the picture out the way, let me get back to the lesson real quick. All right. Now let's say that I was a computer, right? This is how the computer would draw the diagram. very nicely, as you can see. We have our dots there, very accurate, and our line of best fit, which is the blue line right here. Okay. Not asking you guys to draw like a computer, but just showing you that, right? So let's get back into this. After they gave us the data, they asked us to do two things. They asked us to draw a scatter diagram, which we did. And then now just want to go over the interpretation of the scatter diagram. So we got it right here, it's the same diagram. All right. So by inspecting the figure, right, we see that smaller values of x are associated with smaller values of y, and larger values of x tend to be associated with larger values of y. Roughly speaking, the general trend seems to be reasonably well represented by an upward sloping line segment as shown in the diagram. All right. So that's the whole point of this. We're looking for trends. All right. We're looking for trends. So, of course, it is possible to draw many curves close to the points in Figure 4.1, but a straight line is the simplest and most widely used in elementary studies of paired data. We can draw many lines in the figure, but in some sense, the quote unquote best line should be the one that comes closest to each of the points of a scatter diagram. To single out one line as the best fitting line, we must find a mathematical criterion for this line and a formula representing, the line. This will be done in the next section, right, using the method of least squares. Another problem precedes that of finding the best fitting line. That is the problem of determining, right, how well the points of the scatter diagram are suited for fitting any line. Certainly, if the points are a very poor fit to any line, there is little use in trying to find the best line. If the points of a scatter diagram are located so that no line is realistically a good fit, then we say that the points possess no linear correlation. Excuse me. We'll see some examples of scatter diagrams for which there is no linear correlation. So here you go. Let me show you guys some examples. And to be honest with you, mathematically speaking, right, if we take the point and if we take an individual point and we measure that point from a line of best fit, like a straight line of best fit, there is always some type of linear correlation in practice going on, right? But depending on the shape of the data, the a straight line, right, may not be the best line for all the data that you're looking at, right? But just know that in practice and in reality, pretty much all data sets have some type of linear correlation going on, right? Now, let's look at these. We have A and B, right? I could plot a line here, but it's not clear which way to go with that, right? Should it be negative? Should it be positive? It's not crystal clear, right? And also for B, like this, yikes, I haven't seen that many dots since chicken pox, right? It's not really clear if that's a positive correlation or a negative correlation. So if the points seem close to a straight line, we say the linear correlation is moderate to high. depending on how close the points lie to the line. If all the points do in fact lie on a line, then we have what's called perfect linear correlation. That's if they line up straight with the line, right? So in this next figure, right, we're going to see some diagrams of perfect linear correlation. In statistical applications, perfect linear correlation almost never occurs, right? So this is like strictly a theoretical thing that I'm about to show you guys, right? When I show you the perfect correlation. All right. So first I'm going to show you guys moderate, then we're gonna go into perfect, all right, which never ever 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 happens. All right. All right. So the variables x and y are said to have positive correlation if low values of x are associated with low values of y, and high values of x are associated with high values of y. Right? This next figure is showing you that in a picture form, right? Parts A and C show scatter diagrams in which the variables are positively correlated. On the other hand, if low values of x are associated with high values of y, and high values of x are associated with low values of y, the variables are said to be negatively correlated, right? Otherwise, the line of best fit has a negative slope, right? So here we go. So these are two scatter diagrams with moderate, what you call it, linear correlation, right? Notice that the dots are scattered all over the place. They're not on line, right? This is why this is moderate linear correlation, right? So this would be positive. You see how the line is increasing from left to right. And B would be negative. You see how the line is decreasing from left to right. Again, the dots are scattered, right? Now let me show you perfect. All right. Again, this almost never happens. I've never seen it happen in real life. You know, you would need like some kind of like setup with some kind of situation that's like done on purpose, to do something like this. But this is what perfect correlation is like, right? Notice that the dots, they are still scattered, but they're on the line in a perfect straight line. This is perfect linear correlation, right? So this one, obviously, C would be increasing from left to right. So that's positive, perfect linear correlation. D is decreasing from left to right, right? So that's perfect negative linear correlation. All right. All right. So now let's look at that mathematical criterion, shall we? So what does a scatter diagram tell us? A scatter diagram shows the relationship between two paired variables x and y. For each pair, xy, of the data set, we plot the points on a grid with horizontal axis x and vertical axis y. To the extent the data points on the graph fall closer to a straight line, we say that the relationship between x and y is more linear. To the extent that the data pairs are scattered over the graph, we say that no linear relationship exists between X and Y or is apparent, right? So let's make this a little bit more simpler, right? Let's talk about the sample correlation coefficient R, right? So looking at the scatter diagram, to see whether a line best describes a relationship between the values or of data pairs is useful. In fact, whenever we are looking for a relationship between two variables, making a scatter diagram is a good first step. There is a mathematical measurement that describes the strength of the linear association between two variables. This measure is the sample correlation coefficient R. The full name for R is the Pearson product moment correlation coefficient, named in honor of the English statistician Carl Pearson, who is credited with formulating R. All right. Let's look at how we do this now. By the way, this formula is on your formula sheet, so you guys don't have to memorize it or anything like that. And on your test, you're allowed to use your formula sheet as well, along with your calculator. Okay. So the sample correlation coefficient R is a numerical measurement that assesses the strength of a linear relationship between two variables x and y. R is a unitless measurement between -1 and +1. So in symbols, -1 is less than or equal to R, which is less than or equal to 1. If R is equal to 1, there is perfect positive linear correlation. If R is equal to -1, then there is perfect negative linear correlation. If R is equal to 0, there's no linear correlation. The closer R is to 1 or -1, the better the line describes a relationship between the two variables of x and y. All right? Let's look at 2. Positive values of R, right, imply positive values of R imply that x increases, y tends to increase, right? Negative values of R imply that as x increases, y tends to decrease. It's that simple, right? The value of R is the same regardless of which variable is the explanatory variable and which is the response variable. In other words, the value of R is the same for the pairs xy and the corresponding pairs yx. The value of R does not change when either variable is converted to different units. All right. So basically, like what it's trying to say is that if you swap the x and y variables, right? Like say instead of plotting xy, you decided to plot yx, you're gonna get the same kind of correlation out, right? So nope, hold on one second. One second. Can make that better. I can make that better. So this is just a diagram describing what we just went through. A positive linear correlation, low values of x, low values of x and low values of y are associated together, and high values of x and high values of y are associated together, therefore making linear correlation, right? Right here where it says X bar and Y bar, as you remember, X bar is our sample mean, right? So literally, remember how we had the two lines right there? If you found the mean of the X, for example, and the mean of the Y, right? You can actually plot those 2 points on the graph, right? This is really interesting now, right? The mean, right? The mean of the x and the mean of the y actually lie on the line, right? So remember, I was talking about that line of best fit. It's moving through the points, but it's not actually touching the points, right? Some of the points are closer to it than others, but it's not actually touching the points. There's no point that's on the line, right? But for the mean, right, when you do the mean of x and the mean of y and you plot those two means together, that lies on the line. Really, really interesting. All right. Just want to show you guys the negative one real quick before we move on. Just a little visual to go with all the words that we're speaking about. All right, so here we go. This is negative linear correlation, right? So as you can see, right, low values of x and high values of y are associated with high values of x and low values of y. This is negative linear correlation. Same game as what I was saying before. If you take the mean of the x numbers, right, the average, right, add them all up, divide by how many numbers are there, and you do the same kind of averaging with the y values, and you plot those 2 points, right, that point will live on the line of best fit. All right. Any questions so far before we move on? All right, good, good, good. All right. Just want to show you guys an example of something with little correlation. I don't feel confident in saying no linear correlation, but little correlation, right? So as you can see, right, low values of x, high values of y, there's dots there. High values of x, high values of y, there's dots there. Low values of x, low values of y, dots there. High values of x, low values of y, there's dots there. So it's a little difficult to say if this is a positive or a negative linear correlation, right? We can actually use our R formula to give us that, to tell us how positive or how negative this will all turn out to be, right? But just looking at it, you would say that this is like little to no correlation, no linear correlation, right? If this was a test question and you told me no linear correlation, I would give you credit for this because it's really hard to just definitively look at this and say what it is. So now let's talk about that R formula. All right. So we have our computation formula for R. All right. The defining formula for R shows how the mean and standard deviation of each variable in the data pair enter into the formulation of R. However, the defining formula is technically difficult to work with because of all the subtractions and products, etc., right? A computation formula for R uses the raw data values of X and Y directly, right? So whoever made this, they didn't want to plot their graphs. Instead, they rather just use some kind of mathematical formula to give us whatever the line would be, positive or negative, and how positive and how negative would that line be, right? So this formula is measuring also the strength of the line as well. Also, please note this is the strength of the line. It is not the actual slope of the line. Let me be clear about that. So sometime, well, not sometimes. You remember when we used to do our lines, right? You might have slope is equal to 16. And I'm telling you that the value of R is in between -1 and 1, right? So it's just telling you the strength of the slope, is not telling you the actual slope, right? In relation to data to the data that is given, right? So, procedure. How to compute the sample correlation coefficient R requirements. Obtain a random sample of n data pairs, right? X and Y. The data pairs should have a bivariate normal distribution. This means that for a fixed value of X, the Y value should have a normal distribution, or at least a mound-shaped and symmetrical distribution. And for a fixed y, the x value should have their own appropriate normal distribution. All right. Here's the procedure. This looks crazy. It's on your formula sheet, so don't worry about having to memorize it. All right. So using the data pairs, you want to compute the sum of x. Remember, that's when you just add up all the x values. The sum of y. Again, that's when you just add up all the y values. The sum of x squared. So this is when you square, right? You're going to square the x values and then add them up. And then you have the sum of y squared. This is when you square the y values and then you add up all of those. And last but not least, you have the sum of x times y. So this is what that one is you're going to take the x and the y's, multiply them together, make a new column, and then you're just going to add up all of those, right? With n equal to our sample size, right? So sum of x, sum of y, sum of x squared, sum of y squared, and sum of x times y, you are ready to compute the sample correlation coefficient of R using the computation formula. This is our computation formula for R. It says n, our sample size, times the sum of x times y minus the sum of x times the sum of y, all divided by, this is a double square root, right? The square root of n times the sum of x squared minus the sum of x squared times the square root of n times the sum of y squared minus the sum of y and then squared. Be careful, the notation sum of x squares means first square the x and then calculate the sum, whereas the sum of x squared means first sum the x values, add them all together, and then square the result. All right. Any questions on this formula? Anybody? I know that was a lot to take in just now. All right. All right, so then let's continue. So it can be shown mathematically that R is always a number between 1 and -1. So -1 less than or equal to R, which is less than or equal to +1. This next table gives a quick summary of some basic factors about R. For most applications, you will use a calculator or computer software to compute R directly. Yes, you can do this on your calculator. However, to build some familiarity with the structure of the sample correlation coefficient, it is useful to do some calculations yourself. So for the next example, we're going to show how the computation formula is used to compute R. Okay. So computing R. Sand driven by wind creates large, beautiful dunes at the Great Sand Dunes National Park, Colorado. Of course, the same Natural forces also create large dunes in the Great Sahara and Arabia, right? Not gonna lie, with our snow outside, we kind of got our own dunes going on, but whatever. Is there a linear correlation between wind velocity and sand drift rate? Let x be a random variable representing wind velocity in 10 centimeters per second, and let y be a random variable representing the drift rate of the sand in 100 um what is that, gigameters per centimeter per second, right? A test site at the Great Sand Dunes National Park gave the following information about X and Y. All right, so here we go. Let's talk about some facts about the correlation coefficient. If R is 0, right, almost never happens, practically never happens ever, but hypothetically speaking, let's say that R was 0. There is no linear relationship among the points of the scatter diagram, and the scatter diagram will look like this diagram right here. Bunch of dots, no direction, you don't know what to do, right? Let's say that R is 1 or -1. So that means that there is a perfect linear relationship between X and Y values, and all the points lie on the least square line. So here you go. This is when R is -1. You have every single point on the line, right? And we have a negative slope right here, right? When R is +1, every single dot is on the line, and we have an increasing line here, right? That too never happens in real life either, right? But let's show what does happen in real life. Okay. So here's this situation here, which makes a little bit more sense, right? So if R is between 0 and 1, so that's 0 less than R less than 1, the X and Y values have a positive correlation. By this, we mean that large X values are associated with large Y values, and small X values are associated with small Y values. So as we go from left to right, the least square line goes up, right? This is positive correlation right here, right? Now, let's say that R is between -1 and 0, right? R is between -1 and 0. Then, right, we say that this is going to be -1 less than R less than 0. The X and Y values have a negative correlation. By this, we mean that large X values are associated with small Y values, and small X values are associated with large Y values. So as we go from left to right, the least square line goes down, right? This is negative correlation. All right, any questions on this? Just checking in. Any questions on this? We good? All right. So say we have a situation like this. All right. We have some values for X, values for Y. We want to construct a scatter diagram, and then we want to answer the question, do you expect R to be positive? Yes or no? All right. So let's knock this out, right? You already know what this is going to be, right? I'm going to do a, whoops, hold on. Let me get another color real quick. That's fine. So we're gonna draw our first quadrant, right? Now, I don't have no labels for this, right? So we're just gonna call this X and Y. But if there was some kind of story going on here, I would put some other information there, right? I'll put the actual word of whatever X is and the actual word of whatever Y is. Anyway, looking at the X, right? I see my smallest value is 70, my largest value is 125, right? So I have to have those numbers on my diagram. Do I want to start from zero when the smallest value is 70? No way. So what am I going to do? I'm going to squeeze this graph, right? I want to get to 125. I'm trying to think, how do I want to do this? From 70, I want to get to 125, right? Let's say that this is 70. Um, do I want to go by tens? Let's go by tens. All right, just making it up. So 70, 80, 90, 100, 110, 120, 130. All right. Let me just make sure that I got the biggest number there. I did. All right. Now I'm looking at my Y's. I see my smallest number is 3. My largest is 62. Right. Just want to make sure I capture that. Right. Smallest is 3. Then largest is 62. All right. Maybe I'll go by, I don't know. I feel like I'll go by tens, right? But I'm gonna start this off at 0. Right? Should I go by tens? Let's go by fives. I'm thinking that might be too much. Yeah, I'm gonna go by tens. I'll just estimate it. So 10, 20, 30, 40. Now I know I happen to increase both axes over here by 10. You're in complete control. You can do whatever you want. If you want to increase by threes, you want to increase by fives, you want to go by ones, you're in complete control. Whatever works for you. All right. And let's call that top part 70. Not drawn to scale, but you get the idea, right? So get my other color. Okay. So let's start it off. I have 70 and 3, right? So 70 is here, and I feel like 3 is somewhere like here. Just making it up. Next one, I have 115, 45. So 115, 45. I feel like it's somewhere like here. Next one, I have 105, 21. So 105, 21. I feel like it's somewhere like here, give or take. 82, 7. So 82, 7-ish, somewhere right there. 93, 16. So 93, 16, I think is somewhere like here. Then we have 125, 62. So 125, 62. And then we have one more time, 88 and 12. So 88 and 12, somewhere I'd guess like right here. Right? Boom. So there goes my scatter diagram. right? Next, do you expect R to be positive? So what do you guys think? Would R be positive or negative here? Looking at the graph, what would you say? All right, I agree. It'd be positive, right? And then if I had to do a line of best fit, I would draw something like this, right? Where my R is positive. Here we go. Now, in the interest of time, all right, I'm just gonna avoid making this table, but you guys can make this table as well, right? Let's say that I wrote all of my X and my Y values vertically. I could make this table of values right here. Just to recap how this table came about, in for the X, all they did was they just copied the X's straight across the line, right? Just copy them straight down. That's how you got all these X values here. For the Y, they did the exact same thing, right? Just copy straight down all those values, right? For X squared, whatever number that they had here, 70, for example, they squared it, and then there goes your answer, 4,900, all the way down, etc. Right? For the Y, same thing. Whatever they had for Y here, they just squared that. That was it. For X times Y, they multiplied the X and the Y value together to get that number, going straight down. At the bottom, just add all the numbers in the column. That's all this is. We're just adding up all the numbers from above. All right, just add them up, add them up, add them up. And that essentially is our pieces that we need to calculate our R value. I just want to save time in doing that. And then I want to show you, all we have to do is just plug in those values right here. All right, we just plug in those values, right? We're going to compute R for the computation formula. To find R, we need to compute the sum of X, the sum of X squared, the sum of Y, the sum of Y squared, and the sum of X times Y. It is convenient to organize the data in a table of 5 columns as shown, and then sum the entries of each column. Of course, many calculators give these sums directly. That's true, right? The calculators that we have in class, the TI-84, gives us these sums directly, so you don't have to what you call it. You still have to do the table to show the work, but you don't have to do the sums. Calculator could do that directly for you, right? And then and then you just plug it into the formula, and then that's it, right? So we have R is equal to N times the sum of X times Y, right? Minus the sum of X minus Y. It's minus the sum of X times the sum of Y, excuse me, all divided by the square root of N times the sum of X squared minus the sum of X squared times the square root again of N times the sum of Y squared minus the sum of Y squared. Plug in the numbers, right? The 7 is because we have 7 pairs here. 1, 2, 3, 4, 5, 6, 7. That's where the 7 is coming from. And then the 18,000, right? That's just the sum of x times y right here, etc. You plug in the numbers, little calculator, and then it comes out with 0.949, right? So when we did our graph, indeed, R is positive, but how positive, right? You would say it's 0.949. That's how positive it is. That's how close that R is to one, right? Remember, if it was at one, it would be perfect, right? All right, let's get the determination. So what does the value of R tell you, right? Since R is very close to one, we have an indication of a strong positive linear correlation between the wind velocity and the drift rate of sand. In other words, we expect that higher wind speeds tend to mean greater drift rates. Because R is so close to one, the association between the variables appear to be linear. Because it is quite a task to compute R for even 7 data pairs, the use of columns as an example 2 is extremely helpful. Your value of R should always be between -1 and 1 inclusively. Use a scatter diagram to get a rough idea of the value of R. If your computed value of R is outside the allowable range, or if it disagrees quite a bit with the scatter diagram, recheck your calculations. Be sure you distinguish between the expressions such as the sum of x squared and the sum of x and then squared, right? Negligible rounding errors may occur depending on how you or your calculator round as well. All right. So, an easy way to interpret a graph like this, right? Say I wanted to interpret this, right? You could simply just say, this is for interpret. You could say as x, but don't just use x, right? Use the story, right? Wind speed, right? Increases. I'm just gonna put an arrow because I ran out of space. Y, dune, dune, what was it, height or something like that, right? As x is increasing, y is also increasing. Write out the word increasing. Don't just put arrows. I'm doing that because I ran out of space to write here, right? And vice versa. If it was a negative correlation, you would say as x is increasing, y is decreasing, right? That's the very simplified version. So on your test, when they say interpret these results, that's what we're looking for, right? As x is increasing, y is increasing as well because positive correlation, or as x is increasing, y is decreasing, right? For a negative correlation. All right. So a little recap. So what does the correlation coefficient R tell us? The correlation coefficient R is a simple statistic from a data set of ordered pairs XY. It is a measurement indicating the strength of a linear relationship between X and Y. R is a unitless measurement ranging from -1 to 1, and R value close to 1 indicates that a positive linear relationship exists between X and Y. This means that as x increases, y increases in a linear fashion. An R value close to -1 indicates that a negative linear relationship exists between the x and y. This means that as x increases, y decreases in a linear fashion. If the R value is close to 0, this indicates that the relationship, if any, between x and y is not linear. All right. So a little side note and commentary that we want to talk about. So cautions about correlation. The correlation coefficient can be thought of as a measure of how well a linear model fits the data points on a scatter diagram. The closer R is to +1 or -1, the better a line fits the data. Values of R close to 0 indicate a poor fit to any line. Usually, a scatter diagram does not contain all possible data values that could be gathered. Most scatter diagrams represent only a random sample of data pairs taken from a very large population of all possible pairs. Because R is computed on the basis of a random sample of XY pairs, we expect the values of R to vary from one sample to the next, much as the sample mean X bar varies from one sample to another sample. This brings up the question of the significance of R. Or put another way, what are the chances that our random sample of data pairs indicate a high correlation when in fact the population's X and Y values are not so strongly correlated? Right now, let's just say that the significance of R is a separate issue that will be treated later, right? Where we test the population correlation coefficient rho, and then this is the Greek letter rho, showing you what that looks like. And then just want to show you that real quick. All right, so R, right, that's our sample correlation coefficient, right? Computed from a random sample of XY data pairs. Rho is the population correlation coefficient computed from all the population data pairs of X and Y. So there is a less formal way to address the significance of R using a table of critical values or cutoff values based on the R distribution and the number of data pairs, right? This next problem is going to, at the end of the section, discusses this method. The value of the sample correlation coefficient R and the strength of the linear relationship between the variables is computed based on the sample data. The situation may change from measurements larger than or smaller than the data values included in the sample. For instance, for infants, there may be a high positive correlation between age and months and weight. However, that correlation might not apply when we extrapolate the results to people ages 20 to 30 years. The correlation coefficient is a mathematical tool for measuring the strength of a linear relationship between two variables. As such, it makes no implication about cause or effect. The fact that two variables tend to increase or decrease together does not mean that a change in one is causing a change in the other. A strong correlation between X and Y is sometimes due to other, either known or unknown variables, such variables are called lurking variables. All right. We gotta talk about that. All right. So in ordered pairs, X and Y, right? X is called the explanatory variable, Y is called the response variable. When R indicates a linear correlation between X and Y, changes in values of Y tend to respond to changes in values of X according to a linear model. A lurking variable is a variable that is neither an explanatory nor a response variable, yet a lurking variable may be responsible for changes in both the X and the Y, right? So that's crazy, right? This thing is causing changes to be there that we can't see. All right, let's look at this real quick. All right, I'm gonna run through this and then we'll call it a day at that. But in the meantime, please type your name in the chat for attendance today. I appreciate it. Like, type your full name in the chat for attendance. All right. Causation and lurking variables. Over a period of years, the population of a certain town increased. It was observed that during this period, the correlation between X, the number of people attending church, and Y, the number of people in the city jail, was R is equal to 0.90. Does going to church cause people to go to jail? Is there a lurking variable that might cause both the variables of X and Y to increase? All right, so we hope that church attendance does not cause people to go to jail. During this period, there was an increase in the population overall. Therefore, it is not too surprising that both the number of people attending church and the number of people in jail increased. So, a high correlation between X and Y is likely due to the lurking variable of population increase, right? The correlation between two variables consisting of averages is usually higher than the correlation between two variables representing corresponding raw data. One reason is that the use of averages reduces the variation that exists between individual measurements, right? So we're going to look at another section called the central limit theorem. A high correlation based on two variables consisting of averages does not necessarily imply a high correlation between the two variables consisting of individual measurements. All right. So that's it for today. All right. If you guys haven't done so already, please type your name in the chat for me for attendance. All right. You guys can, if you guys are in class, you guys can just hang out until the end of class. Do start your homework as well. Everything has been posted. You guys can knock that out. As I said earlier in class, I would like to do a test on Thursday, but I do feel kind of bad for the short notice. So let's say next week, Tuesday, we'll do our first exam, right? First exam will cover everything that we did from the beginning up until now. So it will include the scatter diagram, right? Very simply for the scatter diagram question, all I'm asking you to do plot the scatter diagram itself, right? With the dots, give me the the axes as well. Um, the next thing I'm going to ask you to do, I'm going to ask you to estimate what R is. I want you to tell me what you think R will be. I'm not asking you to compute R. I'm asking you to tell me what you think R would be. Do you think R would be positive? Do you think R would be negative? That's all I'm asking. That's the second question. And the third question is the interpretation. The interpretation goes as X is increasing, what is Y doing? If it's positive correlation, Y is increasing. If it's a negative correlation, Y is decreasing. And that's it. It's that simple. All right. So that's it. Um,